So here in chapter 24, we're going to be looking at carbon-carbon bond-forming reactions. The reason that we're doing this is that back in previous chapters, we have talked about other carbon-carbon bond-forming reactions. For example, back in chapter 7, we talked about nucleophilic substitution, doing SN2 reactions, even some SN1 reactions, but mostly it was the SN2 reactions, where we could make new carbon-carbon bonds in that fashion. In chapter 16, we learned about doing Friedel-Crafts alkylation and acylation. So that's where we made new bonds with aromatic rings between a carbon and an aromatic ring. In chapter 17, we looked at organometallic compounds to make new carbon-carbon bonds. That included the Grignard reagent, an organolithium reagent, and the organocuprates. In chapters 21 and 22, we looked at some carbon-carbon bond-forming reactions where we looked at nucleophilic enolates. So we made reactions with the alpha carbon. Well, in this chapter, we're looking at some reactions that just don't really fall into those categories. And since they don't fall in those categories, we're going to kind of put them into this whole new category. These are all coupling reactions. And so I think it's important to do this because it kind of rounds out the types of carbon-carbon bonds that you can do in an organic chemistry, an undergraduate organic chemistry course that maybe you wouldn't have seen in previously. So let's go ahead and look at this, and we'll look at the examples. So just a couple of the types of reactions that we're going to be doing. The first three sections are going to focus on making these new carbon-carbon bonds using halides with some other reagents. In this first section, we'll talk about doing the reactions with organocuprates. We'll make new carbon-carbon bonds. These are very useful reactions. In the second section, we're going to talk about the Suzuki reaction. And the Suzuki reaction uses organoboron reagents with alkyl halides, and again, forms new carbon-carbon bonds. And with the Heck reaction, we're going to be making new bonds between alkenes and an alkyl halide using a palladium catalyst. And so it will look something like this. They each have something to offer that's different than the others. And then after that, in case you're curious, we're going to be looking at doing some metathesis reactions, olefin metathesis reactions. So we'll do that one towards the end. So let's get started with organocuprates. So we can do coupling reactions with organocuprates and alkyl halides. So if we take an organocuprate and we use an alkyl halide, we can also use aryl halides. We can make a new bond between two carbons, and we'll form this. So we had talked about using organocuprates when we were using the alpha-beta unsaturated, when we talked about alpha-beta unsaturated carbonyl compounds, we talked about acid chlorides, epoxides. So we've already used them for some things, but we can take organic halides and make these new carbon-carbon bonds with organocuprates. So when we do this, one of the R groups on the organocuprate is transferred to make the new bond with the carbon, and the other one isn't. It is not. It's essentially not going to be used. So you only use one of the two carbons on here. All right, so when we're doing this, let's look at a couple of examples. They work well with methyl halides, primary halides, vinyl halides, and aryl halides. And those are ones that we were not able to use, the vinyl halides and aryl halides. We were not able to do that with SN2 reactions. So this really gives us a lot of options. So here we can make a new bond between this carbon and this aromatic carbon here, and that's our compound. We can also use it on some secondary halides, but the tertiary halides are a little bit too sterically hindered. And so if we attempt to do a tertiary halide, we may have trouble. We probably will have trouble. As far as the halogen goes, it can be chlorine, bromine, or iodine. And we'll talk about the stereochemistry in a bit, but the stereochemistry when we do this is retained, which is one of the features that I like. So we're going to look at number 1 on our in-class assignment. So we'll switch over here. Number 1. All right, I'm going to lower that camera down a little bit. All right, so we're going to make a new bond, and I think it's useful when you're doing this to indicate where you're going to make the new bond. So we're going to make a new bond. We're going to break this carbon-chlorine bond, and we're going to break this copper-carbon bond, and we're going to make a new bond between those 2 carbons. So we'll have 1, 2, 3, 4, 5, 6 carbons that come from this particular molecule. So 1, 2, 3, 4, 5, 6. And then we're going to have these 2 additional carbons, 7, 8, and that's going to be our product. And in case you're curious, the new bond that we formed was this bond. So that's the new bond that we formed. All right, here we're going to make a new bond. We're going to break this bond, and again, we're going to break the bond between copper and the methyl group here, and we'll make a new bond between that carbon and the methyl group. So this is a pretty easy one to draw. Get that methyl group, and that's it. And just to be consistent here, that is the new bond that we formed. All right, here, this is our bond that we're going to break, and there is the other bond that we're going to break. So we'll draw this portion first, draw our aromatic ring. We'll put our methoxy groups on there. All right, and then in this position, we're going to put 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. And just to be clear, this is the new bond that we formed in this reaction. All right, for this one, I'm going to go ahead and indicate that we're going to break that bond, and we'll break that bond. And when we draw out our new one, we have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. We have a double bond here, methyl there, double bond here, and then this is our new carbon-carbon bond that we formed with this organocuprate. And so that is a sec-butyl group. You can draw it a couple of different ways. I'm just going to draw it the same way that was here. Draw it like that. And so that is our organocuprate. And then again, just to be clear, this is the new bond that we formed. All right. So now, when it comes to using the organocuprate coupling in synthesis, we also want to be able to think about this the other way around. So think about how it is do we synthesize these starting materials, and also what bond did we break to make it. So, you know, like when we look at a product, we want to be able to think about what what was the new bond that we made, and what is going to be the product that we're going to have. So, so we prepare organocuprates in 2 steps from alkyl halides. So we can take an alkyl halide, treat it with lithium, 2 equivalents of lithium. One equivalent becomes the organolithium reagent, and the other equivalent becomes the lithium halide. So that gets lost. Then we treat that with copper iodide. We only need half of an equivalent of this per equivalent of this, and we will get the organocuprate. And then we can take that organocuprate and react it with another alkyl halide. We have a few more options on this, but we can make it with another alkyl halide, and we'll make a new bond between this carbon and the alkyl halide and this carbon. Now, one thing about this is that we only get to use one of these alkyl groups. So we tried to avoid using this on alkyl halides that have taken us a really, really long time to do synthesis on this side, because if we spend a lot of effort on this, we get to this step, we're going to throw away half of these alkyl groups. So if this is a really complicated part, that's going to be problematic. So typically, if we're going to have a really complicated part, it's going to be this alkyl halide, because we use all of this. Well, in theoretically, we would use all of it. So let's look at number 23. Number 23 requires that we look at this a little bit retrosynthetically, but it's just a matter of looking at this and determining what was the new bond that was formed. So here, what organic halide is needed to convert lithium divinyl cuprate? So we're essentially adding a CH2CH to whatever the other portion of our compound is going to be. So we're going to look for wherever the vinyl group is, which is this, and this is the new bond that we formed. And since the CH2CH, that vinyl group, came from this, the rest of it has to come from our organic halide. I'm going to arbitrarily choose bromide, double bond there, bromide, and then that. Now, there's something that's implied here that I haven't really talked about, which is the stereochemistry. We'll talk about that here in a little bit, but that is our organic halide that we have. So now for this one, our new bond that is formed is going to be this bond, which means that this is our organocuprate, and then this part is going to be our halide. All right, and again, I'm going to choose bromine. Arbitrarily, we could have chosen iodide or chloride, but I'm going to choose bromine there. All right, for this one, we need to identify what our new bond is. It's going to be right there. This is the vinyl part that comes from our organocuprate. So we need the CH2, that benzene ring, and that methoxy group all in our alkyl halide. So methyl, CH2, and then there's our bromine. And then over here, we'll have the OCH3. All right, we'll use that plus that organocuprate, and then that will give us that particular compound. So pretty straightforward synthesis and pretty easy to kind of analyze and go backwards with. So next, we're going to be looking at the Suzuki reaction, and it is the first of two reactions that use a palladium catalyst and that have an intermediate organopalladium compound that is used in the way. The second reaction that uses the palladium catalyst is going to be the Heck reaction, and we'll talk about that one in the next section, but for now we're going to look at the Suzuki coupling reaction. So what's involved with the Suzuki coupling is that we'll use an alkyl halide and an organoboron reagent. And so the boron is bonded to some sort of alkyl, aryl, vinyl group. There's any number of possibilities that this could be. And we're going to make a new bond between this alkyl group and that R group. So we'll have a new carbon-carbon bond. The boron's going to make a new bond with OH, which comes from the hydroxide. And then the halide, this halide is going to end up as an ionic compound with the sodium. So there we go. So that is that's sort of the basics of it. Let's look at it. Let's look at the palladium in a little bit more detail. Now, I have limited ability in this course and limited time to go over organometallic chemistry in full. So if you take another course later that is on organometallic chemistry, you'll talk about this in much more detail. But we're going to talk briefly about Palladium ligands. And there are several of them that are based on phosphine that are very useful to use. But in addition to the phosphine ones, there are other ones. So let's talk about the phosphine first, the phosphine ligands first. Phosphine ligands tend to be good electron donating ligands. It is possible to get electron withdrawing ligands. We can see that at a later point, But here, this one is triphenylphosphine. We've seen triphenylphosphine before when we were talking about the Wittig reagent back in the chapter on aldehydes and ketones. But here we've got we've got triphenylphosphine. We've got a variety of triphenylphosphine that's called the triorthotolylphosphine, and it's got an extra methyl on there. It does make it a little bit more sterically hindered. And then here we've got the tricyclohexylphosphine, which is this. All of these are good electron donating ligands, but there are other ligands that are electron withdrawing ligands. So when it comes to the organopalladium compounds, these are compounds that are going to have an organic component where we have a carbon that is bonded to palladium. So we'll have a covalent bond between carbon and palladium. We usually prepare these within the reaction. In situ just means in the reaction itself. So we don't prepare it separately and then dump it in. We prepare it in the reaction itself. So these reagents often have acetate ligands, like this is palladium 2 acetate. So acetate is a moderately electron withdrawing ligand, or phosphine ligands like this one. This one has 4 triphenylphosphine ligands on it. In most of our reactions, we're not going to need a full stoichiometric quantity of palladium. We're only going to need a catalytic amount. And that's a good thing because palladium is not a cheap reagent. And so we use a catalytic amount, and sometimes we find ways to recycle that catalytic amount of palladium. It's a good thing to know. And so if we have a general ligand, like if we're just talking generically about a ligand, we can often use the letter L to indicate a ligand. And ligand is just something that's attached, like in this case, it's something that's attached to the metal. So palladium bonded to 4 ligands, we can indicate as PdL4. So that L is not a specific ligand, it is a generic ligand. Now there's 2 key reactions that happen with the palladium compounds. And those 2 key reactions are called oxidative addition and reductive elimination. The oxidative addition is where we add a reagent, and here an example is that we have an alkyl halide. We can add that to the metal. So here we've got palladium with 2 ligands on it. We're going to add the Rx to that palladium. Essentially what's going to happen is we're going to make a new bond between the R group and the palladium, and a new bond between the halogen and the palladium. And so this is called oxidative addition. Reductive elimination is where we eliminate 2 groups that are on the metal. It's sort of the opposite of this. So with reductive elimination, we may have an R and an H, just as an example. So we have R and H attached to the palladium. When we do the reductive elimination, we're going to lose this. We'll have a new bond between the R group and the hydrogen, and we'll be left with our PdL2. That PdL2 can then go on and react with another compound. So there's lots of possibilities for this, and we will look at some of those possibilities. So let's look more closely at some details of the Suzuki reaction. So the Suzuki reaction is a palladium catalyzed coupling reaction between an organic halide. Doesn't necessarily have to be an alkyl halide, but it's an organic halide. That organic halide is usually going to be bromine or iodine, not so much chlorine. And then our other thing in the coupling reaction is an organoborane. The organoborane will have a carbon-boron bond, and then usually something with oxygen here that is bonded to that boron. We'll look at some specific reagents here in a bit. In the course of doing that, all right, so our typical palladium catalyst that we're going to do is going to be this palladium with 4 triphenylphosphine ligands. All right, and it's carried out in the presence of a base like sodium hydroxide or ethoxide. And if it's done in the presence of sodium hydroxide, when we do this, that hydroxide will end up being bonded to the boron. We'll get a new bond between the carbon here and the carbon there. And then this halide is going to end up as an ionic compound with sodium. So that's what happens to all of the components. One cool thing about the Suzuki reaction is that it is stereospecific. So if we take a vinyl halide and an aryl halide, both of which have a halogen group bonded to the sp2 hybridized carbon, and then we're going to have the halogens are usually bromine or iodine. Again, chlorine is not usually used, and fluorine definitely not used. So here we've got this aryl halide, and then here is our organoborane. And then the point of this is that when we do this reaction and we have a specific stereochemistry in this organoborane, that stereochemistry is going to be retained. So we don't lose that stereochemistry. We end up, if it's E here, it'll be E in our product. So we'll make a new bond between this carbon and the carbon on the aromatic ring, and our stereochemistry is retained. In this particular case here, we've got this carbon, and again, we've got this E stereochemistry in our organoborane. That E stereochemistry is retained. If we have a particular stereochemistry on our vinyl bromide here, this one happens to be Z, so it's a cis isomer there, and we combine it with this E, we're going to have Z for this one and E for this one. So the stereochemistry from our components is retained in the product. And that is a very, very cool feature. All right, we want to look at preparing the Suzuki reagents because that is something worthwhile to know. If I just say here you have a Suzuki reagent, you need to know how it is do we make these Suzuki reagents. So we can prepare vinyl boranes and aryl boranes, but we have to prepare them in slightly different manners. The vinyl boranes are going to be prepared by doing hydroboration of an alkyne using something that's called catechol borane. So this is the catechol borane. It has a boron-hydrogen bond. You may remember hydroboration of alkynes from way back in chapter 11. If you don't, go check it out. All right, so you can do the hydroboration of that, and we'll find that the boron and the hydrogen add to this terminal alkyne in a syn fashion, which means that they add on the same side. So the consequence of that is that the R group and the boron are going to be trans to each other. In other words, we'll get the E vinyl borane. Aryl boranes are prepared in a slightly different way. We'll need an organolithium reagent, which we know how to do. So we'll take that organolithium reagent, we'll react that with a trimethyl borate, and that will give us this aryl borane. And then that aryl borane can be used in a Suzuki coupling reaction. So let's look at number 4. Number 4 is on 2 pages. When I was setting this up, it just didn't quite fit onto 1 page. So I'm going to do it on 2 pages here. So here I have an alkyl halide and this organoborane. And one of the features is that the stereochemistry of this and this are going to be retained. We're going to break this carbon and this carbon. And when we break those carbons, we're going to make a new carbon between here and here. So we'll break this bond and this bond. I think I said break carbons. We don't break carbons. We break bonds between this and this, this and this, and we're going to make a new bond between this carbon and this carbon. So we have 1, 2, 3, 4. So 1, 2, 3, 4, double bond and methyl. That's this component. Our new bond is going to be between here and this carbon. So that's that new bond. We have a double bond there. So that's 1, 2, 3, 4, 3, 4. And that is our product. So that is the product of this Suzuki coupling. All right, and there's some other products, and I'm not primarily concerned with those other products. I'm primarily concerned with this product. All right, we're going to do the same thing here. Instead of having a vinyl borane, here we have an aryl borane. So we're going to break that bond and this bond, and we'll make a new bond between this carbon and this carbon. So I'm going to go ahead and still draw this one first. So 1, 2, 3, 4, double bond. We're going to keep the stereochemistry. So our new bond is going to be trans to this CH2. So that'll be our new bond, our new carbon here. And that new carbon is going to be this benzene ring. All right, there's nothing else attached, so that will be the entire compound. So 1, 2, 3, 4, and then there is that. And again, the stereochemistry from this, since this is E, this is also going to be E here. All right, let's look at C and D on this particular problem. All right, so this is what's happening with this reagent. Well, when we take an aryl halide like this bromobenzene, that is going to make an organolithium reagent. So in step 1, we're going to make the organolithium reagent where we have lithium instead of bromine. And then that we're going to react with this trimethyl borate, and that will give us our aryl borane, which we could then use in a Suzuki coupling reaction. So we're going to break this bond here, and we're going to make a new bond between this carbon and boron. So this particular question, all right, I got a little sloppy there, but that's a benzene ring. And then we've got boron OCH3 2. One of our methoxy groups is lost from that borane when we do this. All right. We're also going to get a lithium, in case you're curious. We'll get a lithium OCH3. That may be relevant as far as what happens when you're working it up or when you're using it with something else. So that may be relevant because that's a pretty strong base. All right, on this one, this is hydroboration. Again, we first saw hydroboration way back in chapter 11 when we were looking at alkynes. And here, the hydroboration, the boron is going to go to the less substituted carbon. So we will end up with all right, and we're going to make a new bond between this carbon and boron. And then this hydrogen is going to go to the second carbon on that terminal alkyne. So we'll get a carbon-carbon double bond, and then boron. We'll go ahead and draw the other components of this, the rest of that this is the catechol borane. All right. And we will get the E stereochemistry at this carbon-carbon double bond. And then this we could use in the synthesis, doing a Suzuki coupling. All right. Yes, before we go on, I need to switch back here. All right, so this is the Suzuki mechanism. And I don't show you the Suzuki mechanism so that you necessarily can reproduce it and give it back to me. Like if I see you on the street, I come up to you and I say, hey, can you show me the mechanism for the Suzuki coupling? If somebody does that, it's not me. And so that's an imposter. It's not me. But the reason I show you this is to help you understand what's going on. So the organohalide will do oxidative addition to our palladium compound. So typically we'll have the palladium with the 4 triphenylphosphines. We'll lose 2 of those triphenylphosphines and we'll get this palladium with 2 triphenylphosphines. We'll do the oxidative addition, so we'll get a new bond between our carbon and our halogen. New bond between our carbon and palladium and between the halogen and palladium. Then our nucleophile, which is our organoborane that reacts with hydroxide, that will act as a nucleophile and will displace our halogen. and we'll get this particular reagent. Then we do the reductive elimination, and when we do that, we're going to get a new sigma bond between this carbon and this carbon, or at least that the first carbon there and the first carbon there. That will be our coupling product, and what's left over is going to be this, which can go on and do another cycle. So it truly is a catalytic process. For every one of these palladium molecules, we can do hundreds, maybe thousands, maybe even more of these processes. So we don't need a stoichiometric quantity. And as I mentioned earlier, that's a good thing because palladium is not cheap. All right, so let's look at a couple of examples of doing a Suzuki reaction. And so the Suzuki reaction, you can use it in a case like this. This is called Bombicol. I may be saying that wrong, but that is the name of this. So here we've got this E. So we'll have that E stereochemistry there. Here we've got Z stereochemistry on this vinyl halide, and we retain that stereochemistry. You see, we get the new carbon-carbon bond between those. I mean, that's almost like magic. It's not magic because, you know, there's an explanation for it, but it seems like magic because you just take a couple things, throw them together, and we get this out. We can also do intramolecular Suzuki reactions, so that's something that is quite useful. So here we have our alkyl halide and our borane here. They're in the same compound, and we can use our catalyst to make this, which is called humulene. So when we're doing synthesis with the Suzuki coupling, what the very first thing we want to do, the very first step, is going to be determine what new carbon-carbon bond was formed. Once you know what new carbon-carbon bond is formed, one half of it is going to be your alkyl halide or aryl halide or vinyl halide or whatever, and the other half is going to be the borane. And so determine how to make that borane. So in this case, this particular component would be our vinyl halide, and if you have a component that is if you have a cis stereochemistry, that's probably going to be the vinyl component. The trans stereochemistry is pretty easy to make with the hydroboration. The cis, not as easy. So we'll use the hex 1-ine and our borane catechol. Our catechol borane to make this, or to make our boron reagent. And then this will be the other part, and we'll make a new bond between this carbon and this carbon. Let's kind of break it down. So first, we'll take this compound, which is our catechol borane, and it reacts with our terminal alkyne via hydroboration. That gives us this, which because it does syn addition, we'll get the E isomer, or the trans isomer here of that borane. And then when we combine it with this, we'll get the coupling reaction, and we'll get our product. So hydroboration with the catechol borane to form our vinyl borane, and then coupling, the Suzuki coupling, will give us that as our product. So let's look at number 7. And with number 7, we want to figure out how to synthesize these. Let me switch over here. We want to figure out how to synthesize this compound using these starting materials. So it's a good idea to identify what carbons here are which carbons over here. So I'm going to number these. I'm just going to arbitrarily number from left to right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know what happened to my 6 there. Our new bond is between carbon 5 and carbon 6. Now, if we look, we've got 5 carbons there, 5 carbons here. So the two sides are essentially the same structure. So there's probably more than one way to make this, but we're just going to take this. I'm going to call this carbon 1, 2, 3, 4, and 5, and we're going to take this and convert that into react that with our catechol borane to make our organoborane, and then we'll take that organoborane and react it with this. So let's start with this compound. So 1, 2, 3, 4, triple bond gives us that, plus H boron. All right, there's that 5-membered ring, and then there is a benzene ring here. So when this does the hydroboration across that carbon-carbon triple bond, we'll end up with 1, 2, 3, 4, 5, double bond there, and it will be the E isomer where we get this boron, and then our 6-membered ring there. So there is our organoborane that we're going to use. We're going to take that. All right, it's got a little helicopter action flying over my house. All right, we're going to take that, and we'll use this reagent. All right, we'll react that with this, and that will give us our product. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Double bond between 1, 2, 3, 4. Double bond between 4 and 5. And double bond between 6 and 7. And then here, just to be clear, this was carbons 6, 7, 8, 9, and 10. So those are those. All right, so there we go. That is how we did that. There is our chemistry. All right, with this one, we're making biphenyl. Our new bond is clearly this. So our new bond is clearly this. We're going to take this aryl halide, so iodobenzene, and we're going to react the iodobenzene. We're going to react that iodobenzene with lithium to give us the organolithium reagent. So I'm going to just simply take that and react it. So iodo, react that with lithium, and now we're going to get the phenyllithium. All right, we'll take that and react it with the trimethyl borate, which is just going to be BOCH3. That's our trimethyl borate. And then that is going to give us our organoborane. So we'll have a boron, and then OCH3, 2. We're also going to get the lithium methoxide as a side product, in case that's relevant. And then this, we're going to react with another mole of our phenyllithium reagent, our organolithium reagent. No, not with that. I said the wrong thing. It's the iodide. It's the iodine. It was that helicopter that flew over, I think, that did it. And then our product is just going to be biphenyl. Now, if you would ask me what is the most efficient and cost-effective way to make biphenyl, I probably would not say this. I would probably say there is definitely an easier way to do that. For one, biphenyl is something that occurs naturally in petroleum, so in tar. So this is not something that you would probably spend this kind of effort to make by itself. However, if you had certain substituents on there, that might be something that you would be interested in. So again, we're looking at a general class of reactions, not new ways to make biphenyl. This would be among your more expensive ways to make biphenyl. All right, let's look at this last one. And again, we're going to try to identify what is the new carbon-carbon bond that is formed over here. And the new carbon-carbon bond is between this and this, so it's going to be here to here. So this is our new carbon-carbon bond that is formed. And since we have these as starting materials, that means that we need to find a way to add some functional group here. And that functional group would help if it were a halide, preferably bromine or iodine. Fortunately, we know how to do that. We can take this compound, so that methoxybenzene, which is also called anisole, we can take that and react it with bromine, Br2, and when we do, we're going to get the bromide. All right, and then this we can react with lithium. We can react that with lithium, and when we do, we will get an organolithium reagent. That lithium reagent, the organolithium reagent, we can now react with the trimethyl borate. So boron OCH3, and when we do that, we're going to get our organoborane. All right, so that's a pretty straightforward synthesis of that organoborane. Now we can use that organoborane plus our Suzuki catalyst, which is the palladium with the triphenylphosphine, and we can treat this. So we'll just take this with our palladium triphenylphosphine, that, and our sodium hydroxide, and then also this reagent here. And when we do that, we're going to get this particular product. So 1, 2, 3, 4. 1, 2, 3, 4. Double bond there. We've got that methyl there. And then here we'll have the OCH3. So the OCH3. So now let's look at the Heck reaction. I like the Heck reaction because, again, it seems like something that shouldn't be taking place, but using the magic of palladium catalyzed coupling reagent. So we're going to use a palladium reagent, and we can take a vinyl or an aryl halide, and we can couple it to an alkene. So this either needs to be vinyl or aryl. It doesn't work with the alkyl group, so it needs to be vinyl or aryl, and we can couple it to an alkene. The alkene can either be it can be ethylene, which is a possibility, or it can be a monosubstituted alkene. The cool part about this is the new bond between this and the alkene is not this carbon, but it's this carbon here at the end. And so we will get that particular carbon. So our catalyst is palladium 2 acetate, which is this, and we use a palladium. We use the triphenylphosphine. This particular one is the triorthotoluylphosphine. That's the one that has those methyl groups in there, but that's our typical catalyst. And then we carry it out in the presence of a base, which is like triethylamine is a typical base. We do need to use a equivalent of this, so we need to use a stoichiometric quantity of that triethylamine, but the other stuff we can use as a catalytic amount. And so we can get a new bond between this carbon and the carbon that is on the end here, and we get that. Again, it's really cool, and it is kind of, not necessarily what you would expect just looking at it. So the alkene can either be ethylene or a monosubstituted alkene. So here are a couple of examples. These again, your halide needs to either be an aryl halide or a vinyl halide. Here is with ethylene. We're going to make a new bond between this carbon where the bromine is and the carbon here. But again, we're not getting rid of that alkene. We're just removing a hydrogen and making a new bond there. With this one, all right, so in the halogen's usually that. Let's see. If we do have a substituent, the substituent on your alkene needs to either be a phenyl or an ester group, so a carbonyl with an OR, or a nitrile. Those are good possibilities. And so I've got the ester here. This one's methyl acrylate, and then here we've got this vinyl nitrile group here. And so we can do a coupling reaction here between this, and we'll get a new bond there. We do a couple of reaction between this and this, we'll get a new bond there. And you'll notice that we always get the trans alkene. So we're always going to get the E stereochemistry. And any stereochemistry we have with our vinyl halide is going to be retained. So we get E stereochemistry there as well. So let's look at number 8. So here, draw the coupling product when each pair is treated with our catalyst and our equivalent of the triethylamine. Again, I think it's useful to come in and identify which carbons are going to be bonded to each other. All right. So we're going to bond this carbon and this carbon. And the stereochemistry on this carbon-carbon double bond is going to be trans. So we'll go ahead and do this. We'll draw our benzene ring. All right, so this is the new bond between this carbon and this carbon. So here, this is this carbon. And we'll have trans stereochemistry. We'll get a benzene there, and then this will be the E isomer. We will not get the Z isomer. And just in case you're keeping track, this is the new bond that we formed. So again, let's identify the carbons that are going to form a new bond. So we'll get a new bond between this carbon and this carbon. We're going to retain the stereochemistry here, so I will be opposite the ethyl, our new alkyl group, or this carbon will be opposite that ethyl. So let's go ahead and draw this component first. 1, 2, 3, 4. We've got a double bond there, a methyl there, and then our new bond is this, so that's the new bond between this carbon and this carbon. We're going to retain the stereochemistry there, so we will have a double bond, or a carbon-carbon double bond there. And then this is the bond that goes to our phenyl group. And then we want to keep that methoxy at the same position. And then as far as keeping track here, this was the new bond that was formed. Pretty cool. We're going to do the same thing here. Here we've got it turned around. We're going to take this carbon and we're going to make a new bond with this carbon. Now note here that the stereochemistry on this is Z, so we are going to retain that Z stereochemistry on this particular component. So I'm going to draw this part first. We'll do 1, 2, 3, 4. So this is this bond, this, and this, there, and there. And then we're going to retain that stereochemistry. Since this is Z, we're going to have Z here as well. We'll have a carbon-carbon double bond, and then this is going to be E, so we'll have our cyano group right there. So that will be the product between these two. And this is the new carbon-carbon bond that was formed. All right, finally on this one, can I scoot that up a little bit? We'll identify the components. So our new bond is going to be between this carbon here and that carbon there. On the vinyl halide here, we do have the E stereochemistry, so we're going to retain that, and that our new carbon-carbon double bond is going to have the E stereochemistry as well. So I'll draw this component first. Got a double bond there. And then we're going to draw this double bond. So 1, 2. All right, and then this is this bond. So we'll have a carbonyl there. And then OCH3. And that would be our product. And then just to be clear, that is our new carbon-carbon bond that was formed in this Heck coupling. All right, so now go back to this, and we're going to finish up talking about the Heck reaction. So using the Heck reaction in organic synthesis. So to do this, you need to determine, so here we're thinking retrosynthetically, you need to determine, first of all, what alkene and what organic halide were used. And so you want to figure out what new carbon-carbon bond was formed. So locate the carbon-carbon double bond that is adjacent to either an aryl group, an ester group, or a cyano group as a substituent. So we're looking for like this component. And then the other bond is going to be the new bond that we formed. And then the R group is going to be either our vinyl or aryl halide. Right. So let's look at this as an example. So here we've got this aryl group, we've got this cyano group, and there's a double bond. So clearly this is our cyano with our vinyl group there. And so this was the bond that we formed a new bond between. And then here, this is where our halide would need to be for our aryl halide. So once we identify that this is the bond here, that's going to be our alkene, and then this will be our aryl halide. So it's pretty straightforward, but you just kind of have to remember, you know, this reaction in addition to all the other reactions that you've learned. So it's not that this is hard, it's that you've got a lot of stuff that you have to learn. All right, so let's real quickly look at the Heck mechanism. So we have our palladium catalyst. So here's our palladium catalyst with our tri-aryl phosphine ligand. We do oxidative addition of our halide, our aryl or vinyl halide across that palladium. So now we have a carbon bonded to palladium and the halogen bonded to palladium. And then we're going to get a reaction that will substitute, or that will add to this. And we'll get, so it'll add to the palladium, and then we're going to get a new bond between this terminal, the terminal carbon here, and the R group, and then between this carbon and the palladium. And then we're going to lose our product, which is that coupled reaction. We'll get this, and then we're going to do reductive elimination to get rid of the H and the X. This H came from our alkene, and the X came from our alkyl halide. So the X came from the alkyl halide. All right, let's look at number 25, and that we'll make that the end of this video. And in our next video, we'll talk about carbenes. I'm really excited to talk about carbenes. So switch over here. All right, so we want to convert styrene, so that is our alkene. We have an aryl alkene attached to that. So this is going to be the carbon, and just so everybody's clear, that is styrene. So once we identify where styrene is in this, and it's pretty clear here, we got styrene, styrene, styrene. Once we identify that, then we can identify what bond we formed. And we formed a new bond here, here, here. So that's pretty easy. And so we just want to identify what this had to be, what halide that had to be. Pretty easy. Just replace whatever this carbon is with a halogen, and you've got it. So in this case, bromine. And it needs to be bromine or iodine, so we can't do chlorine. All right, here, 1, 2, 3, 4, 5, 6. Got a double bond there. And then here we'll have a bromine. We'll make a new bond there. And then on this one, notice the stereochemistry won't change. So 1, 2, 3, 4, 5. So those 5 carbons. And then a bromine there. All right. Well, that is the end of our first video. In our next video, we're going to be looking at carbenes.